This is the class on motion of charged particle in an electric field. We are going to prove that if a charged particle enters an electric field, then it will describe a circular path. Our problem is to find the deflection produced in the charged particle when it goes out of the electric field. And in the second diagram, you can see that on the screen at which point it will strike. All these we can determine. Okay. At the same time, it can be proved that the deflection this deflection starts from midpoint of the portion between the two extremities of the charge plate. Okay. And here, obviously, due to the capacitor plate, the electric field is going downward. I am drawing a separate diagram for it. If this is your capacitor plate, this is positively charged plate, this is a negatively charged plate. When a charged particle enters, it may be positive, it may be negative. If a positive charged particle enters at this point, then it will go down. If electron enters, it will go up. In the diagram, it is shown electron, because electron moves in a direction opposite to the field. So by following a circular path, it will go out of the field. Our problem is to determine the deflection produced in it when it leaves the field. Okay? When the charged particle is leaving the electric field, what is the angle made by it with the horizontal? This we are going to determine. This angle we are going to find. Okay. Before finding this thing, we make some assumption that charged particle be Q. Its mass is equal to M. It enters with the velocity U. Okay. And the strength of electric field, which is directed vertically downward, B equal to E. This field is due to the plates used in diagram. The field is directed from upper to lower one, and the strength of field is equal to E. So the charged particle, either it goes away or goes towards the field, will experience a force which is given by what? The force experienced by the charged particle will be equal to Q into E. The acceleration of the charged particle, F by M. This thing is going to be equal to QE by M. When the charged particle reaches the point P, then at the point P, this is your x-axis and this is your y-axis. Let the coordinate of this point P be x, y. Okay. I can take it here also. The coordinate of this point be x, y. This part is x and this part is y. With the help of this x and y, you can prove that the trajectory is a parabola. Okay. If it enters with the speed u, then initial velocity in this direction is u, strength of field is e, so its acceleration along the direction of field or opposite to the field we have found. This motion along y-axis will be due to the acceleration QE by M. So after time t, the horizontal displacement, displacement along x-axis will be u into t. And the vertical displacement y will be equal to half a t square. A is nothing but QE by M into T square. This be number 1 and this is number 2. So let us eliminate T from 1 and 2. Eliminating T between 1 and 2, what do I get? Y equal to QE by 2M into T square. What is the value of T? T is X by U. I have taken this big U just not to confuse you. Okay. So this part going to be T equal to X by U. So T square is going to be X by U full square. So this implies Y equal to QE by twice MU square into X square. So this path is obviously parabolic since Y is proportional to X square. So the path followed by the particle will be a parabola. Path followed by it will be a parabola. All of you understand? At the point Pxy, Y and X related this way, so throughout its motion, it will happen this way. Okay? Now your problem is to find the deflection when it goes out of the field. You can have this diagram, it's a nice diagram. Our problem is at the extreme point, at one end of the capacitor plate, what deflection it suffers, this we want to find. Now before we start, if we find the position of the particle, that is obviously determined by 1, 2, and the path is determined by, we'll be referring it in future, number 3. Now the question is, what will be the velocity of the particle when it leaves the region of electric field? Electric field obviously restricted in the portion between these two extremities. When it leaves the extremity, what will be the velocity along x-axis and velocity along y-axis, that we want to determine. So let us find velocity after time t at an arbitrary time. Now can you tell me what is the time taken by the charged particle to travel from this part to this part? They have taken arbitrary negative charge. I am not taking, I am writing q charge here. Okay. So the question is, how long it takes to travel this path, L distance, because that's something like projectile motion, projectile thrown at some angle. Gravity will not affect its horizontal motion. So the velocity with which it started, that they have taken Vx, I have taken u. With the velocity u they have started, the particle has started, this velocity will never be affected. So what is the time taken to travel this path? Time taken to travel this path, going from this end to this end, time taken will be t is equal to, we can take big T for this. Time taken to cover this path is T is equal to L by U. Okay. So let us find velocity. If we try to find velocity after time t, that also we can write velocity after time t. Velocity after time t will be Vx is equal to u. This will not change. Number 4. And Vy equal to A into T. This will change. What is A over there? A is QE by M into T. This is velocity after time T. So what is the velocity? Velocity when it reaches the other extremity, the other end of the capacitor plate. It is started from this end, then at the extreme point, to find the velocity, I need the help of this time. Time it takes to cover this path is L by U. So Vx, this is not affected at all. This will remain U. But Vy is going to be changed. Vy will be A into capital T. This is QE by M into capital T. Okay. So if anybody wants to find the expression for this angle theta, so angle of deviation is going to be with theta. So tan theta is going to be Vy by Vx QE by M into T by U. Okay. This value of T, all of you know, it is L by U. So theta is going to be tan inverse QE by M into U, L by U. So on passing through this, the angle of divergence becomes QEL by MU square. Okay. So by using this equation, in this equation, when you put x is equal to L, the value of y you can get from there and angle theta can be stated from there also. Okay. That I am going to explain. With the help of this also can be done. So tan theta we got. Tan theta expression also we need. Tan theta is how much then? Just I write there. It is QEL by MU square. So tan theta going to be QEL by MU square. Okay. Now the problem is, what is the vertical distance it travels along the screen? We have kept a screen over there. What distance, I mean at which point it will strike on the screen SC? Obviously it is going this manner. At this point it goes this way. Straight it will strike there. Now what is this point Y? Can you find? Of course you can find. Before that, let us see what is the distance of this point where the produced part of this intersect. Can you find it? If we take this is the extremity, this part is Y, then this distance we need to find. If the distance from this end to the point where theta, the produced part, intersect, that distance be x, this distance be x, then this part going to be what? This part going to be L minus x, isn't it? So if the produced part of this direction of final velocity magnitude is what? V equal to, what is the final velocity magnitude? That you can find from here. The final velocity magnitude we got from here. This is shown here, this V. Final velocity magnitude is root over Vx square plus Vy square, and it makes an angle theta with the horizontal. This theta is the angle made by V. Theta is the angle made by V with the horizontal. Now our problem is to prove that this distance x where the produced part intersect, actually where deflection starts, that will be half the length. This is very interesting to note that we will go for that calculation. Okay. The assumption I made over there, this distance from here deflection start, that distance I have taken as x. So this part going to be L minus x. Or we can see in the diagram that tan theta has two values here. You can write here what you are going to prove. To prove that P, this point be P. To prove that P is the midpoint of the line segment of length L. This part length, its midpoint, this we have to prove. Can be proved easily. Tan theta, you see, tan theta going to be what? In the diagram, it is y by L minus x, isn't it? But y we have got earlier. Y is there in this expression. This y I have got another expression. When I put x equal to L, I will get y. At the extreme point, y will be QE by twice mu square into L square. Okay. Twice m at the extreme point. After covering this, we get QE by 2mu square into L square. So tan theta, I have got two expressions now. One I have got here in terms of angle, in terms of velocity, tan theta is equal to this thing, QEL by mu square. Another expression we got here, tan theta is equal to y by L minus x. Just substitute there. This y value you substitute here. QEL square by twice mu square L minus x, and tan theta what you have got here. What is the value? This you put QEL by mu square. This you can see that all these things getting cancelled, QEL getting cancelled. So left part there is L by what? L by twice L minus x is equal to QEL by mu square totally get cancelled. So this implies x is equal to L by 2. So the produced part of this from here, if you join, it will be the midpoint of the portion between these two. This will help us to get the value of y. Just by using trigonometry, anyone can determine if the screen is, the way they have shown here, if the screen is kept at a distance d, then where it will strike on the screen, that point is y dash, say, you can find easily. This y dash. So let us go for that calculation. Let the charged particle strike the screen at a distance y dash above the screen. Okay. This part y dash, we are going to find the value of y dash there. See, this just the diagram we go through to find y dash. So our next problem is to find the point to find the point where the particle strikes the screen. This we are going to find. That be y dashed. So in figure, y dashed by, how much is that distance? All of you can see in diagram. This distance is d and this part is L by 2. You can see the diagram because you have proved this P is the midpoint. So y dashed by d plus L by 2 equal to tan theta. So y dashed going to be d plus L by 2 into tan theta. Tan theta value you already got in terms of those given quantities. You substitute there. That is QEL by mu square. Everything is given over there. So by using this y dashed on the screen where it will strike, that you can find. Okay.